You're muted.
Oh. Yeah, thank you so much. I was muted, so thank you. Thank you for reminding me. Yep. So again, I will repeat what I mentioned. We will have some examples today about the static equilibrium, and then we will discuss very important question that I received from one of you guys. It is a very important question, and I will receive I will share the answer with you. So that's very nice. I will just do double check and make sure that you can hear me. So if you can hear me, just respond yes, just to double check. Yes. Thank you. Appreciate it. Thank you so much. So let's see, guys, what we will study for today. I will move this camera a little bit forward so you can see all of that. So of course, we will have some examples today about the static equilibrium. It looks like very important topic, guys. So you need to understand that, and also that can help you to do lab number 8. And then, guys, we will talk about the angular momentum, and then move to centripetal acceleration and tangential acceleration, and try to show you my typo last session. So I did a typo here, and I prefer to fix this typo, and you know that typo, guys. So you know the correct equation, okay? And then we will move to the moment of inertia example. So we'll have example about the moment of inertia. And then if I go a little bit down, as you can see here, guys, so we will discuss like moment of inertia for different shapes. So moment of inertia should change by changing the shape of the object. So we need to know that. It is very important. And then, guys, we will have a very nice simulation. I couldn't have good supplies to do demonstration, but the simulation can show you what will happen. It is very nice simulation, and it will show you that, guys. And then lastly, guys, and I'm very, very happy that I received question from one of you. That was yesterday. And I'm happy to explain this question for you. I encourage you guys to ask me like the questions about the topics that you don't understand, so I can include them in my sessions. So that will help me a lot. So here I included my answer for a question from one of you guys. So this is very nice. So we know what we will study for today, and that's very nice. But the first thing that we will do, guys, today, I'm going to have some examples about the static equilibrium. It is a very important topic, and you should know how to solve problems like this. So let's go together here and have the first example. So this is the first example, and I will be close as much as I can. So you can see all of that. I will adjust the camera a little bit so you can see the whole whiteboard. So that's very good. This is the example that we will discuss, guys. And I will keep my eye on the chat. So maybe you ask me any question. If you did that, I will be happy to answer you guys. And you still remember last session. So one of you asked me to repeat something on the whiteboard, and I went through that again. So this is totally fine. You can stop me anytime and tell me, please go through that again, and I will be happy to do that. Okay, so let's get started. with this example, and I'm going to explain this example, guys, to you. So here, guys, we have a wall. So this is a wall right here. Here, we have a beam. So this is a beam, like maybe a piece of wood or piece of metal, for example. So we have a beam right here. We have a wire that connects this end of the beam with the wall, so that can keep the beam horizontal. That is very nice. And at this point right here, we have a man, and this man, of course, has a weight. We know that, but it is located at a distance d from this wall right here. Okay, and you can see, guys, that the total length of this beam is L. So the total length of this beam is L. The man actually at distance d from the wall, and also the angle between the wire and the beam is 53 degrees. So this is very nice. Let's see now the problem, like asking about what? The problem, guys, is asking about the tension force. So since we have a wire right here, we should have tension force. And I prefer to keep this a little bit closer so you can see what I'm doing, guys. Okay, so the problem is asking about the tension force. This is what we need to figure out first. And then, guys, the problem is asking about the value of the force that the wall exerts on this beam. So there is a force from the wall exerted by the wall on this beam. So we need to figure out that as well. So if I try to draw all of that, so what I can do? Of course, we have tension force in this direction. So this is very good. And the wall should exert force on the beam in this direction. So maybe I call that R, for example. This is the force that the wall exerts on the beam. That's very nice. And also we know that the man has a weight. So we have W man times gravity. It works downward. So let's see now the forces that we have. Tension force, the wall force, and the weight of this man, which is very good. Now, guys, if I try to redraw all of that, just to keep the forces and help you to see the free body diagram. So let's do that maybe right here. I will go a little bit right here, guys, and work on this side. And I will try to show you how to draw the free body diagram. Always free body diagram represents the objects that we have in the problem, and also the forces that act on these objects. This is simply the free body diagram. And I'm going to do that right now. So we have this beam. I will draw the beam right here. That is very nice, which is this beam right here with the length L, of course. And we have force exerted by the wall on this beam right here. And also I have another force here, which is tension force. So I will draw that as well. So I have tension force also right here in this direction. And of course, we have the man at this point. So the man has weight W man times gravity. Okay. But guys, I forget a very, very important thing here to add. If you know what is that, so you can tell me what is that. If you don't know, so I can answer you. I forgot a very important thing here. Very important component here. So we forget to include the weight of the beam itself. So the weight of the beam, goes down exactly from the center of mass of the beam. So maybe here we have W beam times gravity. Okay, so that's very nice. And it has distance L over 2 from this point. Okay, so I will include that right here. So we have W beam times gravity. This is simply the free body diagram. So 1 force, 2, 3, 4 forces. What is the first thing that I need to do, guys? The first thing that I need to do, guys, I need to know these angles, because I need to decompose these two forces. So I have X component and Y component, and that can help me, guys, to use the equation of summation over torque. So we are lucky to have 35 degrees from here, but we don't know the angle right here. So I will keep it just theta. And now I will decompose these forces. So upward, I will have here T as a magnitude, sine 35 degrees. And in this direction, I will have T as a magnitude and cosine 35 degrees. That's very nice, guys. We decompose the first force. Now I will come to the force that was exerted by the wall. So what I will have here R sine theta in this direction, and here I will have R cosine theta. This is very nice. Now let's come to this free body diagram and try to choose a reference point as mentioned in the lab manual. So the lab manual used those two expressions, pivot point or reference point. So you can use reference point if you would like. Before I create the equation of summation over torque is equal to 0, I need to choose here the best point for me. So the best point for me, guys, that can ease everything, it is actually to be right here. Why is that? Because I don't know this angle, and maybe if I have the reference point right here and eliminate the force due to the wall, that can help me to find something. So I will try to do that and see what will happen. So I'm going to choose the reference point to be right here, and then create the summation over tau is equal to 0 equation. Let's do that. Similar to what we did in the lab. Okay. And if we look at to this equation, guys, so we can see that we should have here like one component, 2, 3 components. Sorry, one term, 2, 3 terms. Why is that? Because we have one force here, 2, and 3. Those are eliminated. This one is horizontal, so we don't need it. This will be canceled. And why canceled? Because the angle between this component and horizontal is 0, and sine 0 is 0. So this will disappear. So we don't need it. We just need those 3 forces. Okay. The distance from this point, the reference point, and the man weight actually is D. So we can do the following, guys. So we can do, again, another mistake here. We can do mass of the man and mass of the beam. Yeah, so that's correct. Again, the same mistake here. So mass of the man and mass of the beam. So that's correct, guys. This is a force and this is a force. Now we need to have force, which is mass of the man times gravity times the distance d. So that will give me the torque. But what is the sign here? We need to think about the sign. Again, guys, apply the same idea, the right-hand idea. So we have D going in this direction. So D cross weight. So D cross weight, that will give me torque in the whiteboard. So we need to have negative sign here. The same thing here. The distance from this point to the weight of the beam is L/2. Here we have L/2. From this point to the center of mass of the beam. So to figure out the torque, we need to do L/2 direction like this across the weight of the beam. So L/2 across the weight of the beam, that will give me torque inside. So the torque is going toward the whiteboard, and we will have another negative sign here. Mass of the beam times gravity times L/2. What is L/2? L/2, guys, actually is the length of this beam divided by 2, because we are considering the center of mass of the beam as a point represents concentrating the mass. So the mass is concentrated right here at the center of this beam. So that's very nice. I'm missing here just one term, which is tension force. So if I look at here, again, I have L, because the distance from here to here is L. So I have L cross tension sine angle. L cross tension sine angle, so that will give me torque in this direction. Yeah, because also the component can represent a vector. Okay, so you can do cross product, guys. So here we will have plus, we have T, we have sine 35 degrees, and we need to multiply that, guys, by L, which is the whole length here. So we have L. And that is, as we mentioned, is equal to 0. So this is very nice. We have this equation, and I will see, can I figure out the tension, which is the first question in this problem. So we know M, according to the problem, of course. We know the mass of the man, we know gravity, we know D, we know the mass of the beam, we know gravity, we know L, we know this angle, we know the length of the beam, of course, but we don't know T, which is the tension force. Now we can solve for the tension force, guys, and I will come right here and maybe go a little bit down and finish this problem for you. Just go a little bit down right here. Yeah, and finish this problem right here. So now if I solve for tension force, you can see that tension force is equal to, let's see, we have here, if I move, I will move this to that side a little bit, so I can go through this again. If I move this term and that term to the left-hand side, I will have positive and positive. And that's equal to T sine 35 times L. So this is what I will do here. So when I do that, I will have M man times gravity times D plus M beam times gravity times L/2. That should be divided by sine 35 degrees times L. And I will have here some numbers here for you guys. So yeah, let's assume that the mass of the man is, let's assume that it is 70 kilogram. The mass of the beam, it can be 50 kilogram. That's possible, made of strong materials, even though it has less mass, but it is made from strong material that can hold the man. We know gravity here. We know gravity here. Let's assume L is 8 meters. So L is 8 meters. D maybe 2 meters. That's very nice. And we have again here L8 meters. Let's see, guys, what we can do. I will bring my calculator. It is right here. And just work with you guys and see what we can do. So I have here 70 kilogram times 9.8 times 2. So this is the first part. And then plus, open parentheses, we have 50 kilogram times 9.8 times 8 over 2. So that will give me 4. That times 4. So this give me, it's hard to see that, but I have 3,332. So I have that number right here. Now I will divide this number, guys. I will divide this number by sine 35 times 8. Let's see what will happen. So we have 726 Newton. And that's very, very, yeah, this is very high force, but yeah, so T is equal to 726 Newton. So this is the tension force, guys. We could manage to figure out the tension force, which is very good. And if we go back again to the problem, which is right here. Yep, and go again a little bit up. So you can see, guys, that the tension force that we have right here was found. So we have 726 Newton for the tension force. And this is very nice. And what we used to figure out that, we used the idea of summation over torque is equal to 0. And we know that the whole system here is balanced. So we can just choose reference point and then try to analyze based on that reference point. This is what we did, guys. Yeah, I will continue, guys, now, just to figure out this force right here, which is R. And see the chat. Maybe you have a question here. So there is no question. Please, if you don't understand that, let me know, guys, so I can go through it again. This is very nice. What I'm going to do right now, I'm going, guys, to benefit from very important idea. Now, I will go to the linear portion, or if you still remember last session at campus, when I told you that there are 2 rooms and between them there is a door. So you can move from linear motion to rotational motion, do some work here, solve some of the problem, and then move to another room, which is linear motion, and benefit from the equations that we have right here to finish solving the problem. Yeah, so you can move from linear motion to rotational motion, and that can help you a lot, guys. If I go now to the linear motion and consider the equilibrium under linear motion. So if I do that, I always use this idea, which is summation over x forces is equal to 0, and summation over Fy forces is equal to 0. This is the definition of equilibrium under linear motion. Early, we used the idea of equilibrium from rotational motion. Now we are using this idea from linear motion. If I look at to this free body diagram, I can see that there are some forces going up and some forces going down. There is a force going in this direction and there is a force going in this direction. So that means we have y component forces and we have x component forces. And we need to respect the direction of these forces because the force is a vector. So now, what we can have here, so we can have maybe x equation. So let's do the x equation. We have r cosine theta going in this direction, and maybe I can go a little bit close, guys, so you can see me. We have r cosine theta in this direction, and we have t cosine 35 in this direction. So this is one equation. This minus that is equal to 0. So that will give you equilibrium along the x-axis. Now let's look at to y-axis or the vertical components. I have here r sine theta and t sine 35 minus the mass of the man times gravity, the mass of the beam times gravity. And if we have equilibrium along y-axis, so there is no movement along y-axis, so that means this equation is equal to 0. And I will write that down for you guys. I will go a little bit back again and write these equations right here for you. So the x equation is actually r cosine theta minus t cosine 35 degrees. So that's equal to 0. And this is the first equation. This equation is along x-axis. Now from here, what do we have? Here we have r sine theta plus t sine 35 degrees, and then minus we have the mass of the man times gravity minus the mass of the beam times gravity, and that's equal to 0. So this is another equation. So now we have two equations. One of them along the x and the other one is along y. Now, since we have those two equations, the rest of the solution is just using math. We need to think how to solve these equations together. I know t, which is very nice. I don't know theta. I don't know r. I know this angle, 35 degrees. I know the mass of the man. I know gravity. I know the mass of the beam. So the only problem here, guys, is r and theta. And I have two equations with two unknown parameters. How I can solve this equation? So let's see what we can do, guys. The first thing, guys, that I can do, I can move this term to the right-hand side, and this term, and this term, and this term also to the right-hand side. If I do that, I will have here r cosine theta is equal to, and also here, I will have r sine theta is equal to. So I will have here negative sign, positive, positive. Yeah, I still have the same equations, but what I did, I moved this term to the right-hand side and moved those three terms to the right-hand side as well. So that gave me those two equations. Now, you can see it is easy to solve these equations. So what I'm going to do, guys, I'm going to divide, maybe this is equation number 2. I'm going to divide equation number 2 by equation number 1. So that will cancel r. And what I will have something like this. Maybe I go a little bit to this side, or maybe move the camera so we avoid the light. Okay. So I will have sine theta over cosine theta, that's equal to sine theta over cosine theta. So that's equal to mass of the man times gravity plus mass of the beam times gravity minus tension force. And again, tension force here, I need to write 726 newtons because we'll need that. We have here sine 35 degrees. So this is very nice. So that is very nice. And maybe it's a good idea to go a little bit down here, guys, and make this a little bit close to you so you can see the answer. Okay, so this is very nice. I need now to divide the whole thing here by t cosine 35 degrees. You know, guys, that sine theta over cosine theta, so that will give me tan theta, which is very nice. And that's actually is equal to the same thing here. So there is no difference. Okay, so now it will be easy, guys, to figure out theta. So it's not a big problem now to figure out the angle theta. So how can we do that? To figure out the angle theta, guys, you need to do the following. So you just need to have theta is equal to tan inverse and include the whole thing right here. Let's do the calculations, guys, and have a number here. So we can do tan inverse and then have the angle theta right here. Yeah, and please remind me if I forget anything, guys. So we mentioned that the man is 70 kilogram. The beam is 50 kilogram. We know gravity. The tension force here is 726 newtons. Theta is 35. Oh, I think we have theta here. Oh, no, we don't have theta. So this is 35 degrees. So it's a good idea to use theta here. That represents this angle right here. So that's fine. I will do these calculations and see what we will get. So we have here, again, let's do that. So we have 70 times 9.8. So this is one term, plus the other term, guys, we have 50 times 9.8. This is the second term. And then lastly, but not least, guys, we have tension force, which is 726 times sine 35, and then close the parentheses, and that's equal to. I need now to divide that by 726 times cosine 35, and that's equal to. So here, guys, we got 2.68. Now we need to have tan inverse to this number. And if I do that, so where is tan inverse? This is tan inverse. And we need to have this number and then see the angle. So this is the angle, guys, that we have. It is 69.5 degrees. So it's 69.5 degrees, and that's very nice, guys. So now you can see that this angle right here, is 69.5 degrees, which is very nice. So since we know the angle, guys, or the direction of the force that is exerted by the wall, I think it will be easy to figure out R itself. So how can we do that? So to figure out R, guys, I think it's a good idea to come back again here, maybe go a little bit down so you can see me. So it's a good idea, guys, now to come to this equation right here and try to solve for R. So how can we do that? Just divide both sides by cosine 69.5, and that will give you R. I will do that, guys. Just from this equation right here, what I'm going to do, I'm going to do tension force, which is 726 newtons, times cosine 35. So that gives me a number, and then divide that by cosine 69.5 and see what will happen. So now you can see the answer here, guys. So the answer is around like 1,698. Yeah, approximately. So you can see R as a magnitude, guys, is equal to 1,698 newtons. So now we know R, we know T, and also we know this angle. So now let's give you a conclusion, guys. Let's give you a conclusion. Maybe I need to go a little bit on this side. We can see everything. Now let's give you a conclusion, guys. If you have problem like this, the first thing or the first idea that you should have in your mind is summation over tau is equal to 0. So this is the first thing from rotational motion. And summation over fx is equal to 0, and summation over fy is equal to 0 from linear motion. Okay? So these are the first two ideas that you need to have, guys, or you should have in your mind when you solve problems like this, because they will help you a lot. Okay? And oh, I have a question here. Can you remind me how we got 35? Okay. So 35. Yeah, it was 53, but we can fix that from here. Yeah. So that was a mistake. Yeah, let's assume that we have 35 degrees. Thank you. Yeah. So the whole solution is correct. So yeah. So my mind reversed the number. I'm sorry for that. So here we had 53 from the problem, but for some reason, I don't know, I used 35, but the same idea, there is no difference here. Here we have 35, here we have 35, and the whole thing is correct, guys. So, and also here we should have 35 as well. Yeah, 35 degrees. Let's see here. Yes. Yeah, but the original problem was with 53 degrees. Okay, thank you so much. This is a very nice catch. Okay, this is very good. Hopefully you understand this problem, guys. And the idea is to understand those two techniques, to understand how to use those two techniques, guys. Okay, I will have an extra problem for you. And what I'm going to do here, I'm going to erase all of this. Yeah, so this is very nice. I think, guys, I think now we have kind of standard that we can use to deal with the static equilibrium problems. And here I have another problem, just to help you guys to understand, yeah, just to make sure that you understand how to solve this kind of problems. And if we look at this problem, guys, we have a wall right here. We have a ladder right here. And we have the ground right here. So I would like you guys to tell me what kind of forces do we have here. So I will give you just a couple seconds so we can try to finish this example. What kind of forces do you think here we have on this ladder right here? Do we have any forces here? the wall exerts force on the ladder. Perfect. Okay. And I think this force is horizontal. Is that true? Yep. This is very nice. So the wall exerts force in this direction. And maybe I can use here if wall. Yeah. Do we have any other forces? Yes, thank you so much. Yeah. Do we have any other forces here? And by the way, the ladder has center of mass as well. Do we have any other forces here? Any extra forces? The ground exerts force on the ladder. Perfect. Okay, this is a very nice point. So the ground exerts force on the ladder. Let's assume that the ground is not friction, it is not frictionless. It has coefficient of a friction. So that means we will have two forces here. And thank you so much. So we'll have normal force in this direction. So we need to have that. And also we will have friction force, which works in this direction. So this is the friction force. So as you can see, guys, if these two and this force are balanced, oh, by the way, we are missing just one force. Yeah, just notice that. We still need another force. It has something to do with the ladder itself. The center of, oh, on the ladder, gravity on the ladder. Thank you. It goes from here, from the center of mass. Thank you so much. Here we have M ladder times gravity. Yes, you are right, guys. You know how to do this, and I'm happy to see that. Perfect. Now, guys, let's now look at this figure and try to assume something. I will assume that we don't know something and try to work on that quantity to figure out it. Here we should have angle theta. Oh, it's not right here, but it should be here. Yes, angle theta. And I will name this angle like minimum angle. So this is the minimum angle, guys, that can make the whole system here is balanced. And if we look at to this figure, guys, and assume that we know everything, but we don't know this angle right here, is there a way to figure out that angle, which is the angle between the ladder and the wall? Is there a way to do that? My answer for you guys is yes. So there is a way to do that. And I'm going to use my meter stick again and draw the ladder. So I have the ladder as a horizontal line right here. So I know that the ladder is like this, but I have it like this now. So I can draw everything as I want. So I can see everything, guys, organized. So I have X and Y and all of that. But if you try to set X and Y like this, so that will be complicated. You need to set Y like this and X like this. So it's fine to have the free body diagram and have it like this. So we have X in this direction and we have Y in this direction. And you will have these forces here. So let's see what do we have. So we have N in this direction, and we have friction force in this direction. And what do we have else? And we have M ladder G in this direction. So hopefully you can see that, guys. And I have here if wall in this direction. So this if wall in this direction. Okay. And the angle between the wall and the ladder can be, guys, actually taken from here. So this is the angle theta. It is between this line and the gravitational force or the ladder weight right here. Okay, so that's very nice, guys. Now, the first thing that we need to do, we need to figure out reference point that can help me to solve this problem easily. So how can we do that? I have one force, 2, 3, 4, 4. So it's good idea to reduce the number of these forces by taking the reference point to be right here. Okay, so now the normal force doesn't do anything here, and the normal force here doesn't do anything, and also the horizontal forces doesn't do anything. We need to think about this. So here, guys, we should have m ladder times g cosine the angle theta. So this is the first thing. And here, what we should have, now I need to think carefully about that. So theta minimum is here. I think we should have theta minimum, guys, between, yeah, I think that was my mistake again. So look at. I think that's correct. Yes, I think that's correct. So, I can see, guys, that if we come here, so the angle between the wall and the ladder, actually, if this is 90 degrees, so this is 90 minus theta. Okay. And we need to have an angle here to decompose this force. And I need to think carefully about that. This is critical thing, and I need to think a little bit carefully about that. So, this is the wall and this is the ladder. I think this angle right here should equal to this angle right here, I believe. Okay, so if we have theta minimum right here, that means we have theta minimum right here. If I go back, to the idea of the incline, that's a good idea sometimes to have something to think about. We have theta here, and we have mg right here. If we have mg mass, I just try, guys, to figure out, and we always here have mg cosine theta. We always have here mg cosine theta, and we always here we have mg sine theta. So I believe this angle, this minimum angle, guys, should be, yeah, let's correct that. This angle should be this force, so this is theta minimum, and the ladder. If we have something like that, guys, so what does that mean? That means this angle right here now is theta minimum. Okay, so this was my mistake and I corrected that. So we can now come to this figure and keep everything as it is. Just move theta minimum to be right here. And this is theta minimum also right here. So we have m ladder g cosine theta, and here, of course, we will have if wall and sine theta. Yeah, that's very nice, guys. And if we try to do summation over torque is equal to 0, so you'll see that you have 0 from the normal force, you have 0 from the friction force, plus 0 from the friction force, and you have, guys, here L over 2, so L over 2 mg cosine theta, so here we'll have negative. We have m ladder times g cosine theta times L over 2, which is the arm, and then we have L cross F wall sine theta. So now we will have positive, because if we do L cross this force, that will give me torque in this direction. So we have positive, and I have here Fw sine theta times L. So that's very nice, guys. I think we are right. I will move this a little bit far away so you can see that. So we have 0 from the normal force. You know which direction angle to both the forces on that diagram. Yeah, so if you explain your question to me, I will appreciate that, but I will just have this answer for you. If I didn't answer your question, so let me know, please. So the problem in the book tells me that the angle is right here. And by mistake, I have the angle right here, but I corrected my typo and have the angle right here. If the angle is right here, that means the angle between the gravitational force and the y component of the gravitational force is also theta minimum, and that can help me to solve the problem. If the problem is asking you about this angle, so you can work with this angle, figure out this angle, and then subtract this angle from 90 degrees, so you can figure out this angle. So it works, guys, with either ways. But working with this angle, guys, will ease everything, because this angle actually is equal to this angle, and that can help me to have equation and consistent. So that's why. If I didn't answer your question, so please let me know so I can do that again. I can answer the question again. Yeah. So that's very good. So we have 0, guys, from the normal force, 0 from the frictional force, and we have here m ladder g cosine theta L over 2. This is the torque from this force. And we have here F wall sine theta times L, and this is the torque, guys, from this force right here. Now we can solve. We can move this, for example, to the left-hand side. So we can have here m ladder times g cosine theta times L over 2, and that's equal to Fw sine theta times L. So you can see L can be canceled, and you can do, guys, the same idea. You will have here sine theta over cosine theta, and you will have here m ladder times g times 1/2. That's correct. M ladder times g times 1/2, and then divided by Fw times L. And that will give you, guys, tan theta. So the same idea you can see here, that we have m ladder times gravity times 1/2 over force of the wall times the length of the L was canceled, so we don't need that anymore. Yes, so L was canceled here. So we have m ladder times gravity times 1/2 divided by the force exerted by the wall, and that's equal to tan theta. And to figure out theta, you need to do just tan inverse. and you need to have here m ladder times g times 1/2 divided by f wall. And that can help you guys to figure out the angle theta or theta minimum here. The minimum angle that make the whole system here is balanced. Because if I move this force a little bit in this direction or a little bit down, so that will destroy everything. So I need to adjust this force, move it ups and down until I balance everything. It is similar when you move those masses in lab number 8 and try to achieve the balance. So here we are not moving the mass, but we are changing the angle of this force, and that will change the x component and the y component of this force. And if this angle, the minimum angle, was changed, for example, you will see that the whole system will not be balanced anymore. So this is very, very important. Okay, we still have some time here. It's 26. Okay, so hopefully you understand that, guys. Again, focus on those two equations when you do this kind of problems. Summation over force is equal to 0. Summation over torque is equal to 0. That will help you a lot, guys. Okay. So this is very nice. And I'm going here to erase everything. So we don't need this anymore. Okay, now guys, we had two examples about the static equilibrium, and you know, guys, how to solve this kind of problem. So it's not hard, just by considering the equations that I mentioned. Summation over tau is equal to 0, and summation over f is equal to 0. Now, guys, I think we still have here some time. Yeah, it is 27. I think we can talk about, guys, the centripetal acceleration and the tangential acceleration. And to make everything easy for you guys, I will not go through the rigid body diagram anymore, but I will just start from the idea of having the rigid body as a point located at the center of mass of that rigid body, and then work from there. So let's do that. Let's do that. So I will have this a little bit dark so you can see this circle, and then work with this carefully. So let's do that. Okay. So this is the rigid body, guys. This is the mass of the rigid body. And here I'm considering the rigid body as a point mass. Okay. This is the center of mass actually of the rigid body, and the rigid body is rotating around this point 0 and 0. So again, when this object is rotating about this rotational axis, that means the center of mass will start to move in circular path, as you can see here. So we'll have here tangential velocity. And yeah, so we'll have tangential velocity, guys. And also, we will have here radial velocity, which is VR. The radial velocity, guys, it can contribute of this radius here is changing. But if the radius is not changing, guys, that means we don't have radial velocity. So the radial velocity here is 0. But I will have this topic in general and just assume that R is changing. Let's assume R is changing. And then we can set the acceleration from the radial velocity, yeah, to be 0. Okay, so having, guys, tangential velocity and the direction of the tangential velocity is changing, so that will give me, guys, centripetal acceleration, which is equal to v squared times r. And r simply is the radius of this circular path, guys. And last time here I included mass, but that was wrong. There is no acceleration is equal to mass times acceleration again. So that's wrong. That was a typo. And again, guys, we know that v is equal to r omega. When we have r omega right here, so we can have a center of mass is equal to r squared omega squared over r, and this will give me here r omega squared. Okay, this is the centripetal acceleration, guys. This is the centripetal acceleration. Now, if we try, guys, to consider another acceleration, so this is called centripetal acceleration. It was created by changing the direction of the tangential velocity. Now we will consider another acceleration, which is tangential acceleration, that can be created by changing the radial velocity. So that's equal, guys, to r alpha. What is alpha? Alpha is the angular acceleration, and r is the radius of this circular path. Okay, that's very nice. So now we have two accelerations, tangential acceleration for this center of mass and centripetal acceleration. If we are considering the center of mass, guys, r is not going to change. So r is going to be constant. So we don't need to consider that. But if we try to consider like different particles in this rigid body, so that means r will change. Since r will change, guys, so we are not considering just the center of mass. Now we decided to consider each one of these particles of the rigid body. So what does that mean? That means the position vector will change because we are considering different particles in this rigid body. And since r is changing, guys, here, so you need to consider this at. So the acceleration, guys, the acceleration or the linear acceleration for all of the particles of the rigid body should be different, because for particle number one, we have position vector number one times alpha, the angular acceleration for particle number one. Even though all of particles have the same angular acceleration, but they have different linear acceleration. So the linear acceleration is different because each one of these objects have different position vector. I will just check the time. Yeah, so 33, we have just 1 minute, guys. So this is very important, guys. I will try to share this idea with you. The angular velocity, the angular velocity, the angular position, and the angular acceleration are the same for all of the particles of the rigid body. But the linear velocity and linear position and linear acceleration is different from particle to another particle of this rigid body. Okay, if we consider the center of mass for this rigid body, so the whole story will change. We will have something like this. We don't need this. But if we are considering each one of these particles, guys, so that means we need to consider this equation, because AT will be different from particle to another particle in this rigid body, guys. And we will talk about that next session. So we are here. We will try to finish the rest next session, guys. And hopefully we will have some time to solve problems as well. So yes, so we are done for today. How the normal frictional force. Oh, yeah, there's a student here asked me about the normal force. So you can stay and I can explain that to you. Yeah, we are done. You can leave. But I will explain that question for the student who asked me. Okay, let's do that. Yes, again, this is the normal force, and this is the friction force. So what I did, I chose this point right here to be reference point. And when we decompose this to x component, sorry, y component and x component, and also the friction force to x component and y component, since this is the reference point, so what will happen? We know that tau is equal to force times arm, which is r, for example, times sine the angle theta. So if you look at this, you will see that the reference point is right here. That means even though we have normal force, we have the angle maybe 90 degrees, but r is equal to 0. So there is no arm here because the reference point is right here. And the same thing is applied for the friction force. Since the reference point is right here, the torque due to the friction force is equal to 0. And the torque due to the normal force is equal to 0. And that's why I ask you to think carefully when you choose the reference point. Try to eliminate as much as forces before you try to solve the problem. Here, I eliminated the normal force and the friction force, so I don't need to think about them anymore. I just have weight, and I have the wall, the force that is exerted by the wall. And that's why just we have two forces. And you are free to move this reference point, maybe here, here, as you like, but I prefer to have it here to reduce the number of forces that I have. Okay, so the reason is the arm is equal to 0, and that's why. Yeah. Did I answer your question? Would you like me to go through it again? I think that makes sense. Yeah, sure. You are welcome anytime. Please, if you have any questions, let me know. And thank you so much.